Okay, so the title of the talk is Geometric Neurons, and actually, I didn't prepare it alone. I was helped by my colleague and friend Stéphane Breuil, who unfortunately could not come, but is almost here. Well, this is what I wrote. Okay, so actually for that talk, Stephen challenged us to talk about deep learning and geometric algebra. And so since there's not that much work on this topic, this is a more explorative talk that is trying to make any link with deep learning between geometric algebra, but also geometry and mathematics. So this is what I will try to do in this talk. And since it's a kind of exploration, I think in this talk there will be maybe more questions than answers. So what I hope is that at the end we can talk, and I hope this talk can stimulate us. Okay, so right before I start, I like to think a bit about how do we perceive deep learning. So usually when we have a problem, the way to solve it, especially in our community, is just to take a book, some equation, work hard, and find the solution. And it comes out that if you use deep learning, sometimes, not every time, but sometimes the way we perceive it is just magic. And at the end, we have something that works, but we do not know exactly why. And I understand that some people do not like it. So what I hope during this talk is we can try to think about deep learning as something a bit more than magic, and just try to think about how to use it as a tool. Okay, so just to start, I will just take something like 5 minutes. Okay, let me try and start my chrono. So I will start just 5 minutes to talk about a very, very brief introduction to neural networks. So this introduction will be just for very, very few things, not technical at all. So just 5 minutes. Okay, so we can start, I think, just talking by a neuron that looks like a node, actually, with here, for example, 3 inputs, x1, x2, x3, and 1 output. And the output, there's a single output that will have only one answer, and this answer, it will be the sum of all the input, each of them weighted by one specific weight, W1, W2, and W3, plus a bias. Okay, so the formula looks kind of simple. So here I have just 3 entries. And if we want to use this neuron, usually what we do is we fix the weights, we fix the bias, and then we take one input and then propagate it, and then have an output. Okay, so, and if we want another input, we get probably another output. So this is the way we use it. Okay, so maybe one neuron is not enough for this talk. So we will use neural networks. We have maybe a lot of neurons, and usually we want to collect them in layers. So a layer contains some neurons, and each neuron of one layer is connected to all the neurons of the following layer. So this is the reason why this kind of network is called fully connected layers. So here, this is an example with 4 layers, and actually the most important one are the first one, because this is where you put your input, and the last one, this is where you get your result. Okay, so the network, the layers in between are called hidden layers because we just cannot see them, and that's fine. This is not so important. And also something interesting is the design of your network. How many layers should I put? How many neurons should I put? Well, it depends on your problem, your experience, and the power you have. So, okay. So, if we just go back to the previous introduction of the neuron, if we see the input as a vector, and the output and the weight also as a vector. So the first vector would be just the input and plus a 1 at the bottom, and the weight would be all the weight plus the b also at the bottom. And if we just see these two vectors, and if we just do the dot product, actually we get the output. And here, if we just see this formula, maybe for many people here, well, you maybe feel that you're already doing geometry, because here it looks like for the x homogeneous coordinate with 1 at the end, so it looks like a point in or maybe big dimension, but and usually when we have this kind of dot product, well, w and x, it's to express a line, a plane, a hyperplane. So if we just considered this expression in 2 dimension, then we get ax plus by plus c. That can be equal to 0, so it looks like line equation. In R3 will become a plane equation, and in any dimension will be a hyperplane. So here it looks like actually we are already doing geometry, and the weight we want to choose for the neuron is something like we'll maybe choose the best plane that can separate a set of points. So, okay, we already started to do some geometry that will almost, well, be strongly affected by the next step. The next step is an activation function. This is a nonlinear function that is applied on your output, because we don't want to have big output. We want to have something, let's say, for example, in between 0 and 1. So we use that kind of, for example, this is a sigmoid that says that if the value is too big or too small, it will be clamped to 0 or 1. So there's many others like well, many others. Okay. So how to learn? Well, so since this is deep learning, we want the network to learn by itself. So the first thing to do is to collect a lot of data for the problem we want to solve, and we put some data in the input. Okay, and when you have the data, you just feed forward. So you compute the output, and the output of the network may not be what you expect actually. So what you have to do is just to make the difference between what you wanted to have and what you actually have, and then you want to smartly update your weight so that the predicted output matched the known input. So smartly update means back propagation, and this is something, let's say, a bit complicated if we enter to the math. Not so complicated, but maybe not so interesting for this talk. So I will completely skip that point for all the talk, and just imagine it works. And what you just have to keep in mind is that for all the things you use in your network should be differentiable, and that's all. So if you just care of this, that's fine. And how to, well, training long, or may be long, but using usually is, well, not usually, it's much faster. So usually using is fast, and you just put some data, feed forward, and then get your output. Okay, well, that was the introduction, and now I want to, well, give a bit the overview of the talk. So usually when we, in the community, we talk about deep learning and geometric algebra, well, we first think about how geometric algebra can help for deep learning, or can make deep learning a better tool. And this is super good. So this is what I wrote here. When I wrote square, it means you have any input. And when I wrote 3D, well, it's the, well, I wanted to write well, geometric algebra or geometry, but this was too big. So 3D means just we want to use GA to do something and to get another result. So that's a possibility. However, there's something else I think that is interesting. It's how can we use deep learning for GA? So this is another question that usually we a bit forget. So here we may want to use deep learning, well, just to take a problem and get a GA solution. This is the first one here. Or we have some GA expression that we want to understand, or we want to convert some GA to another GA. So that point might be also considered, I think. So let's start with the first part, GA for deep learning. Okay, so the question is how much GA, well, geometric algebra, can we put on deep learning? And here we start with complex numbers. Okay, so so many of the previous talks could explain why complex number can rotate, can do some rotation. Okay, so let me explain it also again, but my explanation is a bit better because I have a drawing. So here, if you just consider well, a complex number in the complex plane, then okay, this is fine. This is well, a plus ib. If you multiply this point by I, so actually this is what you get, and this is, well, mathematically easy to follow. And if you continue to multiply it by I, then you really feel that it's rotating. If you continue, okay, definitely it's rotating again and again. Okay, so now, okay, we are starting to be convinced that actually complex number make a rotation. However, I is a very specific complex number. Maybe we want to try with another one, less specific. So if we just move on polar coordinates, so instead of having z equal a plus ib, we get z equal r and cos theta and I sin theta. Okay, so just in polar coordinates, if we consider two complex numbers and we multiply them, then okay, well, with the distributive on the addition, we get a big part here. The blue part is the real part, and the red part is the imaginary part. But if we use some cosinus laws and rules, then we can simplify it to something like this. And the last line here we can recognize that we have the z1 in red plus something, and this something is actually on the rotation, the angle. The angle have been more theta 2 in the two terms. So it means that actually we rotate, and not 19 degrees, we rotate of theta 2. So that, okay, that's nice. But we have to focus also this R1. So R1 means also we scale, so we have to be careful. So if the module of Z2 is 1, so R2 is 1, then this is a pure rotation, and that's fine. But else we have to be careful of this. Okay, so why is complex number related to geometric algebra? So again, you had this explanation, I think, at every talk. So, but let me repeat again. This is exactly the same explanation, but I just to be very clear. So, if we just consider the geometric product we use in geometric algebra, so for vectors only, it's UV equals inner product plus outer product. Okay, so now the very interesting part is if we start with a Euclidean vector space, so I mean orthonormal basis. If you take two basis vectors, twice the same, EI, geometric EI, okay, we just decompose inner and outer. So the outer will make 0. Well, this is one of the rules of the outer product. And the inner product will make 1 because this is an Euclidean vector space. Okay, so that's fine. This is okay. If we take two different basis vectors, then the inner product will make 0 because they are orthogonal, and the outer product will remain. And actually, this outer product anti-commutes. So if we want to permute these two elements, then we just have to put minus. Okay, so that's fine. And the very interesting one is that one. If you square this B vector, so actually, okay, we'll just square it, so just write it twice. And you may want to permute the two first one, so just change the sign. And then the two in the middle, we could see that it makes 1. This is the first line. Okay, so it makes 1. And then we get minus ij. That also makes 1. So the result is minus 1. Okay, so this result is really, really interesting because it means that we have complex number embedded in geometric algebra and without explicitly asking for it. So it's a kind of hidden gift, I would say. And for those who begin with geometric algebra, this is super useful because your problem may be solved using complex number without you knowing it. So this is always hiding a bit it. So sometimes it's really interesting. Okay. So this is clearly, so complex numbers are clearly geometric algebra. If you want to be a bit more convinced, just consider two vectors of dimension 2. And if you just do the geometric product, well, the inner part will make a scalar, and the outer part will make, well, something related to the I, E2, 1, 2 B vector that squares to -1. So we can replace this one by I. So this is really the imaginary part. Okay, so actually we are doing geometric algebra. So, so now the question is how would it be good or how to use complex number in deep learning. So to introduce this, let's consider a kind of silly situation. Okay, so here on the left, what you get is a point in 2 dimensions, x in, that we want to match to x out. Okay, so this is silly because usually deep learning tries to generalize something, and here we have only one single data. It's kind of silly, but okay, let's consider this problem. So if we use the fully connected layers that we mentioned earlier, then we say, okay, I have 2 entries, so x, 2 dimensions, so x1 and x2 for the in, and 2 output, x1 and x2 for the output. Okay. So we have some weights, we learn, and actually the network will converge to some solution. But this is one possible solution, but actually there's many more. There's many different solutions, and the network will choose one. Okay, so is that a problem? Well, maybe yes, maybe no. But now let's consider exactly the same problem, but with complex numbers. So now the input is a complex number. It has 2 entries. So let's say the real part and the imaginary part. And the weight is also a complex number. Okay, so now we just said right before that if you multiply 2 complex numbers, you do a rotation and a scale. And this is exactly what we get here, a rotation and a scale. So now the solution is unique. So so it gives something clearly different. Okay, so well, if I just quote the author, because the question is it good or is it bad? So if we know a priori that the objective quantities include phase or amplitude, then it's good. Well, basically this is what it is. So yes, actually, maybe this is the first point when we can consider, okay, maybe that's a good idea, but I have to really concentrate why it will be a good idea. Okay, before talking about this, let's continue. And something also we should consider is, about the activation function. Now we don't have only one value, we have 2. So, an easy way to continue is just to use the activation function of all the data, all the real part and the imaginary part, and say that the activation function of result of the imaginary part will become the imaginary part of the result. Okay. So, complex number, they are fine, but Quaternion looks better. So maybe we should consider Quaternions. Okay, so if we want to remind a bit Quaternions, we can just start with the Hamilton rules. So what Hamilton wanted to do is to extend the complex number to 3 dimensions. And he could find these 3 numbers, I, J, K, and with a very nice behavior. And then he could express or present Quaternions. Quaternions looks like this. It looks like a scalar, this is S, plus something that actually looks like a vector, because we have 3 components over these 3 values, A, J, and K. Okay. So, so this is what I did. And again, are we doing geometric algebra? And the answer is clearly yes, because if we use the result right before we had, and just consider a Euclidean vector space in 3 dimensions, then we have 3 B vector, E1, 2, E2, 3, and in 3, 1. And if we just rename them like this, if we just rename, okay, I equals something like this, and etc., what we get is exactly Hamilton rules. So, so that it looks like Quaternions are actually naturally embedded in geometric algebra, and that's super good actually. So this is something also really interesting. You have nothing to do; they are there for free. So this is good. So However, if you feel now I give you enough for Quaternion and geometric algebra, this is not correct because I give you the formula, but I didn't say how to use it. So if you want really to understand Quaternion and dual Quaternion, we have another talk 2 days ago. This is a really good one. So for the video, I think it's good to try this video because I will continue. And so now the question is, okay, well, before the question was just some definitions, but well, only the two first ones are interesting. A Quaternion can be just like we say before, but we can also have imaginary Quaternion that just have these three parts without the scalar, okay? And we can norm them, conjugate, or inverse them. Okay, so now, okay, two kinds of Quaternions, imaginary, general. What can we do for deep learning? So right before we said that an input could be a complex number, but actually it could be also a Quaternion, maybe imaginary one. So it could be imaginary Quaternion, meaning that each input had 3 entries, not 1, 3. Okay, not 2, 3. Okay. So what we also want, usually we like when the output is homogeneous to the input. So we also want the output to be an imaginary Quaternion. So here the weight would be Quaternions. And then, so here, this is one possibility about how to use Quaternion in deep learning. So here, I have the propagation function over there, and let's try to understand it. So here, in red, what we get is the sandwich about how to use Quaternion. So it makes a rotation, okay? Okay, so now we have an input and we rotate it. That's good, okay. So the blue part says that according to the norm of the Quaternion, we may also scale the Quaternion, well, the output. Okay, so that's fine. So what we get after this is an imaginary Quaternion that we rotated and scaled. And then if you do in green plus the bias, that is also an imaginary Quaternion, then you make a translation because you just add 3 components. Okay, so we have scale and translation, so it's kind of good. In terms of geometric algebra, we are not satisfied with usually with this kind of way of writing because this is not the way we like. But still, well, it says what it pretends to do. So, well, that one looks good. 3 properties. Well, okay. So, well, just to be more precise, it looks adapted for 3D affine transformations that could be, for example, color processing or 3D affine geometry. So for sure, it will give some interesting result for this. Okay. Okay. So complex number Quaternions. Okay, but actually in geometric algebra, what we like more is Versors. And Versors, well, it's a family of transformation. So according to the algebra you choose, because we have many different algebra, you may find some Versors. Here, this is a special algebra, conformal geometric algebra, and here we have translation, rotation, and scale. Well, I just put some formula just to make you sure that they exist, but you just don't care. And the very important point is that one here. So all of these transformation consist in a scalar and a b vector, and they all use the same formalism. This is a sandwich, so all the same, but we have something super good. It's super good property for this. The super good property is that it's the same way to transform any object of the algebra. So you don't have to care if it's a line, a point. Actually, it could be a point pair, line, circle, plane, sphere, anything you want. It's the same way to transform it. So if we consider this property for neural networks, it means that probably we could set up a network that can handle several different kind of entries and would be robust to this. So that sounds clearly good. So and that sounds a bit better than Quaternion. Quaternion could just handle Quaternion, it looks like, but here we can handle any object, so it looks better. So how to use it? So there's several possibilities on the literature. So the first one would say, okay, I take as input a multivector. So, well, just if you want to know what is a multivector, there was some super good introduction talks, better than introduction talks actually. The one from Leo, for example, Leo Dorst. So, and then you can understand what is a multivector. What you just should understand here is that if you have d-dimensional vector space, then a multivector will have 2 power of d inputs. So it's a bit bigger. So you have to just be careful of about this. So do not take a too high dimension. But what can happen there is that if you also decide that your weights are Versors, so just do transformation, then that can be cool. Then here what you say is that your propagation function is the sandwich. So now you let the network decide if you want to do a rotation, a scale, a translation, or a combination of them. So that sounds good. Okay, so that was 15 years ago actually. Okay, so some other people consider that a multivector is too big. So okay, we don't need the full multivector. Actually, we may consider only points of the algebra. So here, again, we consider conformal geometric algebra. So here the point is, well, actually yes, we use points, only points. Okay, so that's fine. So input are points. So output should also be points. Okay, but the weight are still Versors, just rotating the points, scaling them, and translating them. Okay, so here you just have to be careful because when you do the sum of points, you may not get a point. So from my understanding of the paper, you may do something after the, well, something to really be careful to have a point at the output. Okay, so that's one possibility, just to handle points. Okay. Some other people have some other good idea. They said that, okay, we still get points as input, but the weight would not be Versor. There will be hypersphere. And so, okay, if we consider the 3D case, it would be a sphere. Okay, and why is it an interesting point? It's very interesting because in conformal geometric algebra, a sphere and the plane belongs to the same family, and actually this is almost the same. So a plane is just a sphere with infinite radius. So it means that we are now extending, well, the property that we see at the beginning, that the weight looks like a hyperplane that separates some points. Maybe a sphere, something a bit curved, would be better. So this is what they propose. So looks kind of really interesting for this. And so the way they compute it is just to say, okay, for each Euclidean output of my point, I take something that this looks like here a distance from the point to the dual sphere. And so it looks like a distance. It's not exactly this, but well, at the end it will behave a bit like this. Okay, so that's a good idea. Okay, I put also that one. So that one technically is not my favorite. It just says, okay, everything is a multivector, and here we just do one geometric product. So this one is not my favorite because I think sandwiching is better. However, this one has a super good property that is here, 1992. So for me, it was amazing to see this. So 1992, it means that at that time it was the, well, early deep learning for me. So well, I feel, well, that's still really something good. Okay, so so if we just make a small consideration of what we just say right now, what are the good property that we may want to use with this kind of geometric algebra for deep learning? Well, here we have a geometric consistency. So we know that the data we compute will conserve some geometric property, and that could be something actually super interesting. Okay, so well, if we know that our problem includes only isometry, affine transform, then maybe this is a super good solution because we can avoid errors and maybe have a faster convergence. So that could be interesting, okay? Another interesting point is here we can compute points, but we see that geometric algebra is robust to handle points, spheres, or any object in the same way. So it means that we can maybe have a network that is robust to several different kind of features with the same network exactly. That would be something, I think. Okay, so this is the good part. So here, when I say cons, there's still one question. The question is, usually, if you force your network to follow your idea, sometimes you're wrong, because the network usually knows better than you what it should do, because it will brute force everything, almost. So, I mean, so sometimes, is it really a good idea to say to your network, you should do that way? So, well, this is a question I don't have the answer, but sometimes, clearly, if you know that your data is purely geometric, probably yes, this is a good idea. You will just help him to find the direct way. And sometimes, maybe no. So here, I really don't have the answer. And I have two remarks. Well, this is what I believe, but maybe you can believe something else. But I think that if we want to be convincing that using this network is a good thing, we should absolutely provide a clear integration to the non-framework like PyTorch or TensorFlow. It should be clear, else no one will use it. So and try it. So this is something that should be really, really good. And just for that part, when I explain it, I feel this is not enough. I would like really to show you which one is the best, what we can do, but actually the literature is maybe a bit young for this. So maybe you have some comments for this also too. Okay. Let me take 1 minute to talk about convolutional networks. So, well, less than a minute because I should hurry, I think. Okay, so if we, well, just to make it brief, if we consider, let's say, an image. So let's say the big array is an image, and if you want to have an intuition about convolution for deep learning, this is how it works. So here we have something like, well, this is written convolution, but this is a kernel. And if you put this kernel, this small array, in front of one pixel, so here, well, the pixel in red, then what you can do is multiply each square of the kernel with the small square of the image right in front, make the sum of all these products, and replace or put the output in the resulting image. So, well, it looks nothing like this. Actually, it's super interesting. So this kind of kernels can do many, many different operations on the data, like gradient or blur or anything. And actually, in deep learning, it means that you only have here 9 parameters to define to compute a completely full image. So only 9 parameters. This is nothing. So this is something really, really huge. So in deep learning, this is intensively used. Okay, so if we want to use them with something else, this is what we could do. So actually, we could, if the input is a complex number, for example, we just can take a kernel with complex number as well and replace the product by the product of complex number. And actually, some people and some good people says that actually this is a super good idea and it works really well. I think it works well, but on very specific problem like signal processing or so. Yeah. Or you can do it, of course, with Quaternions. So say, okay, I have Quaternions, or I have more general multivectors or vectors. Okay, with the geometric product. So, okay, I just go fast here because this is exactly the same as what I said right before. Okay, so so here, what we just say, we're just talking about how we can put some geometric algebra into deep learning. So that's interesting, I think. What I want to show you now is a video about deep learning, fully deep learning, that do not include geometry, but he's doing geometry actually. And just see this, and just try to feel the geometry, and then we can talk about this. So this is about fakes. So if you have and you feel that the girl is not pretty enough, you can put the face of someone else here, and maybe you can be happy with this. Let me try this if it works. So, okay, I would say yes. Open. I just happens a bit. Yeah. Okay, so here, this is impressive, I think. So here, there's no geometry inside. This is just an autoencoder. So here, we are clearly doing geometry because, well, the guy is moving the head, and the head is not flat, so there's some geometry, but still, there's no geometry inside the network. So here, I think there's, we make, okay, so, okay. Sorry. Okay. So there was an actor, and we changed his face to the face of another actor. So it could be done using manually. It takes months, or you can just press a button and ask some deep learning to do it automatically. Almost, well, not automatically, but almost. So this is deep learning that just put the face of someone on someone else. So just by collecting some data. Okay. Yeah. Thanks you for the question. So. Here we have some deep learning that is actually doing geometry because change a face to another one. So it includes geometry, but is not doing geometry. Actually, inside this is just an autoencoder. So so the question here is there's two questions. Do we need actually to put geometry inside because it seems to work actually, but can we help? Actually, if we put geometry inside, maybe it's way better. So I don't have the answer here, but I think there's something to think. Okay, where to put geometry in deep learning? Okay, so I move on to the second part, and the second part is, can we use deep learning for GA? So here I found nothing in the early work. So what I want to suggest you, just divide this topic into two parts. Geometry in one part and mathematics in the other part. So I will start with the math part. And here I'd like to ask the question, what's the primitive of 3x squared plus cosinus 2x? And if you can't remember, you may want to design a neural network to do it for you. And that would be good, actually. So, the usual way to solve that kind of problem is to generate some data, then to design the network, learn, train, and usually surpass traditional methods. This is the way it happens usually. So here, the way to do is first generate some data. So if you want to make a mathematical expression, you need some operators. So here we have binary operators, means you need two operands. And I include some, let's say, geometric product or outer product or anything you want. Unary operators, that could be log, sin, square, what you want, but could be also maybe dual, or if you want to sandwich something, so could be this. And then you may want to put some constant, some numbers, some complex number, or anything you want, and some variables that could be either scalar vectors, homogeneous multivector, or multivectors, anything you want. So here, what you just do is, a very good way to have a random expression is to make a tree. Each node is an operator, each leaf is a number variable. So you can just make this kind of tree, and randomly it works super good. And then once you have your expression, you just convert it in prefix notation just to get a string. Okay, so this is not ambiguous, and you get this. Okay, so when you get this, what you can do is generate data. So here I think I run out of time to just explain you, but this is a very important point, how to generate data. So here they found some, in this paper they found some very interesting way to have some good data. Well, just if you want to, well, maybe just the number 2, if you want to have a primitive, you may take one function, find the derivative, and then you have your couple. But this is bias, there's a bias in this, so well, you should better use integration by part, and this works well. So anyway, what you also have to do is to find a nice model. This is what they did with a really nice one, but not big one, 6 layers. That's not a lot. And after the training, you get the results, and the results are interesting. So if you compare to Mathematica, so for Mathematica, they just cut it after 30 seconds because it turns out that after 30 seconds, the new answers are not really interesting. MATLAB, Maple, and deep learning wins for far. So this is really, I like it. Well, this is interesting, I think. So you may say that, okay, the network will every time provide a solution, but you don't know if it's a valid one. You even don't know if it's the good solution. But however, here, it's easier to test the solution to see if it's a good one rather than to find the solution. So still, I think this is really interesting. So that one, I like it when I see it. I really like it. And for those who want something else that integrals, well, if you like differential equation, I know here in this room some people like it very much. So you can also do this, and then. Again, well, deep learning gets really good results. So, well, that looks good. I just put some example of where the deep learning can find a solution where Mathematica cannot. Okay, so well, just from the paper. Okay, so well, for me that's something that we maybe could extend to geometric algebra. Can we do? With geometric algebra. So here I wrote an expression. I don't know if you can see which one it is. Well, so I just wanted to. I give you 5 seconds more. So I just wanted to see if we can use it in any way. So. Well, the problem I wanted to check. In conformal geometric algebra, you have well, if you make the intersection between a circle and a sphere or a plane, you get one entity that is here in well, green and blue. That is called a point pair. And here, if you have your point pair, you do not directly have these 2 points. You have to make one operation. It looks like complicated, and actually, if you take the time, it's really clear. Well, it doesn't look like it, but it is really clear here what is happening. So for this, there's many good tools also. So just refer to this. And the question was, can we retrieve this solution easily or not? If you don't have any idea about how it works, can you do this? And well, before I wanted to do this, I just think about that sentence. Doing random stuff until your program work is hacky and bad coding practice. But if you do it fast enough, it's machine learning and pays 4 times your current salary. So I kind of disagree. I mean, deep learning is not completely random stuff. I mean, backpropagation is not random. So still, there's random things. Well, the most important one is maybe the beginning or the way you learn. Well, the way you choose your data. But well, here I think only this part is really true. What I wanted to show you is what is brute force. So brute force is exactly what I just to get a try. I asked my computer to solve this problem. So I just give some pair points and try to extract the point. And if you're brave enough to wait for 30 seconds, this is what you get. So you get 3 answers that actually are exactly the same. Well, if you just look deeper, these are all the same. And if you wait a bit more, then you have 43 solutions, a bit more exotic, but all the same. Actually, they are all the same. So the question is, for such problem, do we use deep learning? So for this one, actually, no. Actually, I think geometric algebra has also some good property that makes such convergence kind of fast. So this is also something interesting, I think. So here, still the question is, do we need deep learning for this? I don't know. So maybe we can talk about this later. But I wanted to turn it to something more elegant. So by discussing a bit, almost with Steven, we talk about make geometrical algebra genetic again. And so for those who do not know what is genetic algorithm, this is just a very brief example. So here we want to find, we have some dots and we want to find the shortest path from red to red. So what we can do is just generate some random expressions, so random path, okay, that's fine. And then we will repeat many times the following. First, select the best one. So here, well, the two in gray was not that good, so just discard them. Then do some crossover. Crossover means you take two paths that looks compatible and then try to mix them. And actually, here you can find out that well, the beginning of one and the end of the other makes a shorter path, so you keep it. And you may also want to make mutation, meaning that you take one path, you change something and hope it will be better. So choose randomly, if you want to have your salary better, and randomly move something. Okay, so can we do the same with geometric algebra? So actually, well, generate some random expression, that's okay, that's fine. Selection, I will talk about this later. Crossover on the three nodes, so here I have some blue nodes, and if I just want to change them, that's nothing. So crossover is fine. And mutation, if I want to change some operators or some constant, this is super easy. So no problem here. The problem is actually selection. So here, on that specific problem, you cannot say if, well, the only thing you can say is if an expression is valid or not. But you cannot say if one expression is better than another, well, two wrong expressions or one is better than the other. You cannot say this. So here we have a problem. But there's some situations where you can say this. There's some convex problems. So not that one, but so again, maybe this can open to some reflection to get some convex problem or how to make the problem convex. So okay, okay, and then let's move on to the last part, so the 3D part. So here, the question is, well, okay, can deep learning really handle geometry by itself? So if we get 3D data, can the deep learning can do something interesting by itself without geometry? So let me introduce one famous problem. So here it's just to make animation in video games. So for someone walking. So if you consider that walking is something repetitive, then you can put a phase to this action. So the phase would be to say that if you put the right foot on the ground, then the phase is 0. Then when you put the left one, it's pi. And when you put again the right foot, it's 2 pi or 0. Okay, so and here we want to consider only the skeleton of the animated object. So here we can see more specifically, well, on an animation the phase. Okay, for each part of the skeleton, the position, the speed, and some turning angle. Okay, so. The question we want to ask to deep learning is, if I give you all that things, I mean, position, phase, and so on, and trajectory, can you give me the next step of my motion? Well, then, well, if I'm here, well, then just the following motion. So a new pose, the next phase, and the next trajectory. So here, there's a very nice paper for this that provides one solution. And this solution is amazing, and well, really for us this is interesting, I think. So this is, well, this network is a very small one. There's just 2 hidden layers. So it means this is a very compact one. So it looks like too small actually, and this is too small. So what they did is actually get this network, but they consider not only one set of weights, but 4 sets of weights. Okay, so they say, okay, so here this is the alpha 0, 1, 2, 3. So according to the phase of your motion, they will interpolate between 2 weights, okay, using just cubic splines. So, and then it will provide you the next pose of your work. So, so here, 2 hidden layers. Can it provide some geometry? So it looks not enough actually. So let's get a look at the result. Okay, so here, what is interesting is we can see that so deep learning decide how to move. Okay, and someone have a mouse and say, okay, go that direction, run, walk. So you can walk, you can go backward, forward, you can climb actually, you can also jump, you can crouch. So all of this with 2 hidden layers. You can jump here. So here we have a kind of the same question that we had before with the deepfakes. So it means that okay, let me continue. For that kind of task, this is clearly rigid transform. So, I mean, when you walk, the skeleton will not move, the arm will not be longer. So this is clearly rigid transform. So here it's kind of an evidence that this is a geometric problem, okay? But here the geometry is not used. So again, the two questions: would it help to put some geometric constraint? Would it be faster to converge, or better result, or is it a bad idea because the network knows what to do? So, but again, for me, when I saw this, it was a question. Okay, so this is what I feel. This is an interesting video. Okay, and for the next question, can we extract some 3D data from something, let's say from an image? Then you can get a look at PyTorch theory. That may be a good way to try to put some GA inside. And what PyTorch can be used to is to try to put some geometry from images. So if you just give some images, you can try to, well, put a bit some mesh. So even it does not look like incredible, but well, this is automatic, so this is not so bad. Or you may want to extract automatically the skeleton of some people on an image. So here again, is it 2D? Is it 3D? Is it a geometric problem? Can be. So okay. Okay. So my talk is almost finished. I talk about 2 parts. The first part is, can we put geometric algebra inside deep learning, or can we use deep learning for geometric algebra? And for the conclusion, I would say that well, there's actually some interesting effort to do geometry for deep learning. For example, that website, Geometric Deep Learning, well, with conference, tutorial, code, and so maybe something interesting to get a look if you want to work in that direction. And well, again, this is the same question I asked from the beginning. Okay, can GA contribute to deep learning? So, because we include some geometry, or can we use deep learning for GA for assistance for something, or to optimize some problem that we can check later if it's correct or not? Okay, thank you for your attention. And do you have any answer? Okay.